Thank you for this class, and thank you for allowing us to do this together. And Father, I'm thinking of the choir tour, and people are leaving this weekend and going out for a while, and then there's going to be bang, bang, bang after that on the weekends. And so I pray you give the choir a special measure of grace. I don't know how to do that. I'm not going to tell you how to do it, because I don't know each one, but you can help each one of them, Lord. You can help each one, both in their ministry as they travel, but also, Lord, in what academics they need to pile in and squeeze in there. All the things that are involved in that, Lord, you can help them, and I pray that you would, in a very real way, that you would minister through them and to them. And you do that in the name of Jesus, so it will be legitimate and it would make a difference. I pray. Amen.
Amen.
Okay, so clarification. So 7 p.m. tonight, 7 p.m. Thursday. That'll be the tests are going to happen. I'm going to be here both days, but I'm going to ask you if you have friends. There are two, well, Esong and Gideon are in the async class. So they won't have an opportunity to do this test until Friday. So I'd ask you not to discuss the test with them in any way. But anyway, so those are the only two that are on, won't be able to take it. Otherwise, it'll be happening Thursday at 7, and I'm gonna be here for a while. I'll take stuff to do, so I don't have a problem with that. In fact, I can probably end up grading papers. So that's what we're gonna do. So we will not meet Friday, we won't have class Friday. Friday class, those are counting for Friday's class, taking the test, other than Friday. So, in the paper, some of you have turned it in, but I think I sent out some, I did something to let you know that the Media 4 isn't due until Friday, because I try to, if I was gonna go through it, and we had Friday as a class, that I could discuss it, but I can't, so it doesn't make any difference that I came in early. I mean, I try to think, actually I do try to think about you as a class when I do assignments. The heavy hitters have been done. You have a couple observation papers and a bunch of test questions and the last one is due on the 2nd of May, the article, and that should take you some time. It's worth 200 points. Mm-hmm. So bear in mind, for 100, I mean, this is the last 170 or 125 point to paper. For 125 points, if you give me a paragraph, if you shrink the questions into a paragraph, you can do that. I wouldn't advise it. I just wouldn't. I wouldn't think it would be the smartest thing to do a high point paper as brief as you do something that was worth half or less. You know what I mean? Mm-hmm. So, and what I want you to do is think about it. And so usually a paragraph, some of you can write really concisely, but it's a real skill to be able to do that. And so probably your advantage to write remote one. So, okay, this is what we started on Monday. We're going to continue this. So, what determines the nature of volcanic eruptions? 3 things: temperature, the composition, and the amount of dissolved gases it contains. Those are the 3 things. Viscosity, I just want you to know if you don't. Viscosity, more viscous means it's thicker. Less viscous means it's thinner. So less viscous, that's why the volcanoes that come out of Hawaii or that are erupting in Hawaii. You see sometimes flows, people running ahead of the flows. Well, when they didn't expect, when they were caught, and they could run and run faster than the flow, but the flow was just flowing. If it had been something like Mount St. Helens, they would have been blown away. So, because in Hawaii, the composition, it has a lot less silica, it's more basaltic, it's more ocean floor, which has less silica in it, so it's less viscous, and so it throws up, you know, it's nice to watch, but it doesn't shoot miles into the air. It's more, there are some volcanoes that shoot big stuff into the air, but they're a different breed, just than the Hawaiian. Okay. So, viscosity in magma is a function of temperature, but more importantly, viscosity is directly related to its silicon content. So that connection, viscosity, higher silica content, greater, more viscous, thicker. More silica, thicker, more viscous. The dissolved gases provide the force that propels molten rock from a vent of a volcano. You could say, well, if it's got a lot of silica, it's not going to flow as easily through those vents, because the vents, well, I'll show you a picture in here in a minute. The vents are comparatively narrow, and so if you've got a higher silica content, you're going to usually end up with more dissolved gases. They can't get out of it quickly enough. Like the Hawaiian volcanoes can dispel the gases easier because it's more fluid. So it kind of is it's a whole system at work. But generally speaking, greater silica, more viscous, dissolved gases provide the force that propels it from the rock out of the volcano. It's the gases. Okay, you might need to know that, or remember it. I'm not going to play the song right now. I want to be sure I get through this. And the song is just fun. So, lava flows, basaltic, which would be oceanic primarily. Fluid, low silica, can move fast. And then a couple of things, Pahoe and A, what the kind of stuff that does, I'm not gonna get into that at all. You need to know, you should make this connection, basaltic, that's oceanic, like Hawaii, they're more fluid, less viscous, low silica, and they can move fast. The gases are the major ones. Some of you, oh yeah. Yeah, okay, I'll get into this. The major ones, the question you had on 5, and I'm gonna go over 5 after I didn't, I will go over 5 today. I passed it back to you, so I'll go. So, water vapor, carbon dioxide, nitrogen, sulfur are the main 4. And then others, the book had others, but it had actually, the percentages were in your book. First column, I forgot what page, or the first column down toward the bottom, they had the percentage of each of those major ones, and then some minor ones. Pyroclastic material, fragments, and I'm not gonna really talk about this, you won't, just to tell you, this ash pumice. So, this is the finest, and when you have ash covering, when Mount St. Helens erupted, Yakima, which is in eastern Washington, they had automatic lights that went on in their street lights. Well, the lights went on at 3 or 4 in the afternoon. So they don't usually do that, but the ash fall was heavy. People were dealing with ash fall, hard to breathe with just ash settling. Pumice is a little bigger. Lapilli, I think that's it. A little bit bigger than that, cinders, blocks, and bombs. I mean, it's, you don't want to get hit with this stuff. Well, you don't want to get hit with anything. There are ice, you'll find, there are in some hailstorms, there have been hail that's a couple pounds. You hit with a couple pound piece of hail. If it hits you on the head, you're in another place right away. So, volcano, mountainous accumulation of material from central vent, crater, steep wall depression. The vent is part of between the magma chamber and the crater. Caldera, large summit depression. Here is a picture of this stuff. Very simple. So you got your crater up here. You have lava. This is a magma chamber here. And this is magma, and this is magma, and this is magma, and this is magma, right to here. And right to here. It's all magma, except when it extrudes out of it. So magma is what's inside the volcano, simply put. Magma is on the inside of the volcano. Lava is magma that has come outside. So it becomes lava. There's some chemical stuff that happens, but nonetheless, lava is outside. Lava, 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 but this is all magma here inside. And you have a main vent, you have a secondary, you have so from the vent, you have pieces that branch out. In Mount St. Helens, you had something like this, and that's why it blew off the whole side. So that's what. Active areas of volcanism. Active areas of ocean ridges, when they spread, diverging plates. Adjacent to ocean trenches. Ocean trenches are where it's subducting underneath, and the interiors are plates. So, most active volcanoes are associated with plate boundaries. That's something you should probably remember. And you got shield types, you got volcano types. Shield volcanoes, which are largely basaltic, like in Hawaii, broad, slightly domed. Largest active volcano on Earth is Mauna Loa in Hawaii. When I've lived on Maui, and Haleakala is a 10,000 foot mountain, volcano. And you drive up to a place and then you walk up a switchback. And so you're walking up the switchback and all you're seeing is you're walking up the side. And all of a sudden your eyes look over 5 miles across from where you come out, looking over the thing until the other side. There are clouds out in there. There are clouds in that. It was, when you talk about something taking your breath away, something that's so, I don't know if it would be powerful, but something so, you just, whoa, well, it took my breath away. Just all of a sudden watching this going up the switchback, so I'm always seeing inside a mountain, switch, and all of a sudden my eyes are over and looking across 5 miles to the other side of Haleakala. It's just, it's beautiful. And silver sword, a plant that blooms every 100 years. I mean, it was really cool. Plus, down the mountain, they had mangoes. So that was a plus. If you went up the mango, you could get them going up, you could get them coming down. Anyway, Mauna Loa, that's the one. 5.7, what is it, 5.7 miles? Yeah, big one. And so you can see it's spurting up in the air, but it doesn't burn very high, and it's less viscous. A cinder cone, it's the smallest of them, built from ejective lava fragments, very steep slopes, usually less than 1,000 feet high. So this is one. Some of these cinder cones will form inside the cone of a volcano. Mount St. Helens had a cinder cone that built up, that got to some significant height within the cone itself. And composite are what you have generally where you have oceanic floor subducting under continental, and then inland from that, you have the composite cones. This is Mount Rainier. I live within walking distance of Rainier Avenue, about a mile from my home. So this is, you see this a lot on clear days. You can walk right out on Rainier Avenue and look at Mount Rainier, 12,007 feet, just standing there smiling at you. It's really beautiful. But, so these are, you'd find these composite cones around the Ring of Fire. These are the kind of volcanoes that you would typically find. And there is Mount Rainier. A lot of people climb that. It's a pretty mountain. So, I think that finishes. Does that finish? Mm-hmm. That little portion? Let me get this. I want to go over the, if I can, yeah. Okay. This is number 5. So, okay, what's the difference between magma and lava? Magma is within the volcano. Lava is what is outside the volcano. And erupted, I guess technically, erupted, but my thinking was eruption starts internally and not everything that's erupted gets out. So it's simpler to say lava is what is magma that reaches the surface of the earth. So 3 factors determine the nature of volcanic eruption. Oh. Composition, temperature, and dissolved gases. Those are the 3 things. The more silica, the more viscous. So it would lend itself to stronger eruptions. The temperature, the hotter it is, the less viscous it'll tend to be. And the amount of dissolved gases, because it's dissolved gases that provide the force. Now, I'm saying that for the 3rd time. That pushes a molten rock from the vent, the greater amount of gases contained, the more likely the eruption will be stronger. And that's what you find in composite volcanoes, the ones that are around the Ring of Fire. They are more viscous, they have a lot of more dissolved gases contained within them, so they can't get out the vent, so it takes a lot more pressure to build up, and finally when the pressure is building up, then it shoots out. So it's the gases that propel this stuff. And that's why a volcano fed by highly viscous magma is likely to be greater than one with fluid. So in this one, to get through all of this, basically, to simplify, the more viscous the magma is, the thicker it is, the thicker the magma is, the more resistant it is to flow, the more difficult to force through a vent. And the vents were where you saw that picture, the diagram, you have the main vent, but you have this little side vent. Well, the more resistant they are to flow, the more difficult, more force it takes to get through a vent, the more likely to build up gases, which impedes their upward movement, and the more likely to increase pressure. They all contribute to a more violent explosion. So you should have some idea of those. And then, in contrast, very fluid or thinner magma tends to move more easily through vents, and so does not lend itself to great pressure buildup and pressure and gas buildup. So that's what you see, the Hawaiian volcanoes, just like this, but around the Ring of Fire you see more this building up. That's why they're more explosive. List the main gases, here they are. Those are a point apiece, 70% water. I didn't require you to write the percentage. 7% water vapor, 15% carbon dioxide, 5% nitrogen, 5% sulfur, and then some lesser amounts, chlorine, hydrogen, and argon. So if you answered list the main gases, well, there are 4 main. If you just listed a bunch of them, they're not all main gases, so you might have lost a point on that one. It's not a big deal. What's a ring of fire? Circum-Pacific belt. And so what is the ring of fire? You could say that, and when you did, you probably got 2 points out of 6. But if you were really describing what it was, and in a science class, typically I would expect not just fluff, but what is it? Well, it is this, that's what they call it. The ring of fire and this are the same. It's where most of the world's known active volcanoes are located. The volcanoes in this belt are primarily composite cone volcanoes, large composed of both lava and pyroclastic deposits and volatile, capable of awe-inspiring eruptions. So these things, because they're composite cone volcanoes, they're going to be more volatile and provide greater eruptions. So that would have been extra credit. But I was looking for not only this, but where most of the world's known active volcanoes are located. Their world's known active volcanoes are located. And volcanoes in this belt are alive in composite cone. So that tells me what kind of volcano they are, that there are more of them along this thing than anywhere else, and this is what they're called. So when it asks in your test, where it asks for something that's, when I'm asking you to answer a question and I want you to write it out, and I'm going to have a minimum of those, but I'm going to have more. I didn't have any in the last test. In this test, I'm going to have a couple. So, and that's what I'm looking for. So going forward, you got a bunch of these test questions. This is number 5, and you have up to 16. So they're coming out of your book, but it wouldn't be a bad thing if you have somebody else. I mean, you guys are in the class. You see one another outside of this class. It wouldn't be the worst thing in the world for you to compare and say, okay, this is what I got. Do you have this? I mean, just like writing a paper. When I wrote papers, when I was in school, I had a sweet wife. So after I'd been in school 2 years, then I had a sweet wife. But before she was my sweet wife, I could still ask her to read them and see if they made any sense. If this was a question, she didn't have to know the subject, but she had a sense of, if I was writing something that was incomprehensible to her, then it would do me well to take a look at it to see, is this, if she didn't understand it at all, then I'm not being clear at what I'm writing. And clarity is a good thing. You can color things with not being clear, but so I'm staying here for a minute just because this is a very simple question. What is it? And if all you gave an answer was, and many of you did, this is where you stopped. You didn't go far enough. You got 1/3 of the points possible, but you missed 2/3. Is this right? Is this true? Yes, it's true, but it's incomplete. So in the same way with it, list the main gases. It didn't say list the gases. It said the main ones. Well, there are 4 main ones. It clearly says that in your book. There are more, and it gives them. Chlorine, hydrogen, argon. But they're not main. The main were these 4, and So just to be, in this class, I don't want you to be confused. Minimum answers tend to get minimum points, just saying. Describe the mechanism by which explosive volcano eruptions are thought to influence the Earth's climate. They influence the Earth's climate. How do they do that? Some of you gave me how they explode. But that's okay. You can tell me how they explode. But if you don't tell me how they influence the Earth's climate, then you didn't actually answer the question. I usually gave you a point. I think there were 6 points for this one. I usually gave you a point just for making an effort and typing all that stuff down, all that quotation. But, so how they deal with it, they eliminate, the ones, explosive volcanic eruptions. So those are composite cone volcanoes. Those are the ones like the Cascade Range well, it runs from Canada all the way down into California, but the Cascade Range in the Northwest, they are composite. Most of the ones in the Ring of Fire are composite, and so they have thicker, the lava is thicker, it's got more silk in it, it holds more gases, it's harder to force it up, out of the vents. So they eject dust-sized particles of ash and sulfur dioxide. Two different things. Ash and sulfur dioxide are not the same. You have ash and sulfur dioxide. Ash is like very fine stuff that makes it difficult to breathe if you're trying to do that with it. And sulfur dioxide is a chemical. So the ash particles reflect solar energy. Sunlight comes in, it bounces back towards space. So it temporarily cools the atmosphere, the ash does, but the ash settles down. Eventually the ash will settle out. Yakima, Washington didn't get ash for years and years. It got it for a while, and it's pretty heavy when it happened. Sulfur dioxide can react with water vapor in the atmosphere and produce clouds of tiny sulfuric acid droplets. These particles, called aerosols, can take several years to settle out. So they're like ash, in these aerosols lower the mean temperature of the atmosphere by reflecting solar radiation back to space. So both ash and carbon dioxide reflect sunlight back into space. So it doesn't come down. It doesn't heat our atmosphere. It's reflected back. But ash will settle down, whereas sulfuric acid will attach to little water droplets and produce, you wouldn't see the cloud, but they'd be there, and so as a cloud, they could last for years, according to the book. Now this was interesting. You didn't have this. I'm just going to tell you. The text no longer says this, but it did in early editions. Quote, "The volume of fine debris emitted during an explosive event is not itself an accurate criteria for predicting the global atmosphere effects of an eruption. Rather, it depends on the kind of gas emitted, and in particular, sulfur dioxide. If volcanism is to have a pronounced impact over an extended period, many great eruptions, closely spaced in time, need to occur." Sounds like what would have been happening if you had rapid subduction. The plates were moving rapidly, oceanic plates were moving rapidly apart, subducting under continental plates. You had a lot of activity, a lot of heat, a lot of stuff that was causing volcanic eruptions. So you had volcanic eruptions happening all over the place, not just Mount St. Helens, but all over the place. And some of them, when you read stuff about them, some of Mount St. Helens was teeny. Well, I think that Steve Austin said, comparison, Mount St. Helens was a little teeny volcano compared to what was going on here. So if that was true, this would exactly fit in. It's not proof. It's not proof, but it would fit in. If you had rapid subduction, you would have a lot of volcanic activity. If you had a lot of volcanic activity, it would contribute to a colder atmosphere. And if you had a lot of stuff with sulfur dioxide being extruded into the atmosphere, and it would last for a long years, the idea of having an ice age is not guaranteed, but it's saying, well, this certainly would contribute to it. So the book doesn't say that anymore, because it's still true. It's exactly true. But it pushes against the idea of uniformitarianism that doesn't want to be addressed. So, how does the addition of water affect the melting temperature of rock? And this is important. So, other than subduction, what would be the next significant generating component of volcanic eruptions? Water. Because it's water that is carried down by the subducting slab that causes the slab material that is being subducted to change with temperature and pressure changes that results in melting. And so when it melts, then you create what will become the lava, you create, or the magma. It melts, and as it melts, then it begins to rise. It's got to melt first, it begins to rise. But it starts to melt, it's the water. The water causes the rock to melt at lower temperatures. Most everybody put that down. Just like putting rock salt on an icy sidewalk induces melting. Additional water lowers the melting temperature of mantle rock sufficiently to trigger partial melting. Partial melting of the mantle rock, a certain kind of paradox, generates salt basodic magmas with temperatures may exceed 2,300 degrees Fahrenheit. These hot basaltic magmas are less dense than the surrounding rock and so rise upward. So when they're melted, they become less dense, so they have a tendency to rise. So water is what would be a key component to volcanic eruptions. Okay? Questions? Anybody questions? Okay, so Tonga is a Polynesian country of more than 170 South Pacific islands. So 170 islands in the South Pacific and home to about 100,000 people. It's a remote archipelago that lies about 500 miles east of Fiji and 1,500 miles from New Zealand. So in 2021-22, I think, this Hungahapa submarine volcano, so it's under the water. It's just underwater between two small islands, about 6,500 feet high from the seafloor. So it's under the seafloor here, the islands here. Subduction is here, the Australian plate here. So you've got this going down here. This is a trench, a very deep trench, and you got these islands. So this goes down. As it goes down, the water it carries with it begins to change the composition of the basalt, and it melts. And as it melts, then it's lighter than the surrounding mantle, and it rises. And this is what's happened. So it's located 40 miles north of Tongatapu, the country's main island, and is part of a highly active group of islands in the volcanic arc, a subduction zone extending from New Zealand north toward northeast of Fiji. So that's what this is. So subducting, melting, rising up, condensing here, and then eventually, the pressure is mounting, and finally it blows its top. So what does that do? It started in December and went to 2022. Most recent eruption, December 2021, with gas, steam, and ash plumes rising about 7.5 miles into the air. So that's not like a Hawaiian volcano. It's not just spilling over, it's going up. And I'm gonna do this. This way.
what we do now. Me, my son, and the boys. We could see from here, it was nothing out of the ordinary. And then we see the mushroom was kind of getting bigger.
So these guys are on the boat.
In a couple of minutes,
It's ready. And suddenly the explosions came. I knew what was coming, tsunami. I accepted the fact that we have 3 minutes left to live. I just felt sorry for the boys, my son and the other boys. They were busy taking pictures and laughing. But I knew, you get hit by tsunami, you go to deep water, just go. But the wave is chasing us and coming fast. Now we're in the deep water. We can see the wave come to the other side and hit the main island. It must have gone underneath us. We didn't even feel it. We thought we were now okay, just go home and that's it, but the worst was to come. It started to rain rocks on us. I'm getting hurt. And then, no! Everything went pitch black. You couldn't see your hand in front of you. Everything was dark, no electricity on the island, no electricity, no lights. 3 hours fighting the sea.
Branko and his family had survived the most explosive event ever recorded on Earth. At 5:15 p.m. on January 15th, 2022, satellites witnessed the volcano Hunga Tonga Hunga Hapai blast a cloud of ash and rocks up into the atmosphere. Within minutes, tsunami waves crashed into the South Pacific nation of Tonga.
I ran with my son. I could see that the wave was higher than his house. We saw a huge wave. It came splashing over the top of the church and school roofs.
A boy came and reached out to grab me. I said, "What are you doing?" He said, "I'm going to carry you so we can escape."
Rock and debris rained down on Tonga for over 10 hours, covering the country in a layer of volcanic dust.
So that's this Tonga earthquake, and well, it was interesting to me that they would think, okay, they survived the tsunami, they're good to go, except the stuff that has gone up in the air is going to come down, and for the next handful of hours, that's what it did. And ash is one thing, but as I went over quickly, the things that go down, I mean, you can get boulders coming down, because it shoots all that stuff up. So that initial eruption sent it 7.5 miles up. On the 15th of January, it lofted ash gas and moisture 12.4 miles high and sent atmospheric shockwaves and tsunami waves around the world. The eruption brought powerful tsunami waves in some places up to 60 feet high and heavy ashfall to islands in the nation of Tonga, several damaging coastal communities. So that's that.